If you build a system and run it over and over again, it will never yield the exact same result twice, no matter how tightly controlled the environment is. Absolute consistency is an illusion. Think about your daily commute. You leave at the exact same time, take the exact same route, and drive the exact same car. But one day it takes 25 minutes, and the next day it takes 28. Statisticians call this common cause variation. This chart shows that kind of baseline variation. It's the normal, unavoidable background noise built into the system itself, like catching a few extra red lights or getting stuck behind a slow truck. The results bounce around, but they stay within a predictable corridor. But then, one morning, you blow a tire on the highway, and you're sitting on the shoulder for an hour. That hour-long delay is a special cause variation. It's an anomaly. It doesn't mean your normal route is broken. It means a specific, addressable failure occurred outside the normal boundaries of your daily drive. Now, imagine trying to track millions of these commutes every single day. At a massive industrial scale, how do you distinguish between harmless background noise and a systemic failure? Left to our own devices, we are incredibly poor at interpreting raw data. We are wired to spot patterns, even when we are just looking at random fluctuations. When we rely on intuition to manage large systems, we make two critical errors. We either panic and overreact to normal everyday variations, adjusting things that don't need adjusting, or we entirely miss the early warning signs of a genuine impending disaster. To run a complex operation effectively, organizations need a mathematical filter that can separate the actual truth from the background noise. That mathematical framework is called Statistical Process Control, or SPC. It is a method developed specifically to measure, manage, and interpret all of this variation. For a long time, manufacturing relied on a highly inefficient strategy. Build the entire product, inspect it at the very end of the line, and if it's defective, throw it away or rebuild it. Statistical process control takes the opposite approach. By continuously analyzing behavioral data from the machinery itself, operators can detect when a process is drifting out of alignment and fix the equipment before a single bad part is ever produced. By implementing this math, global industries moved from reacting to damage that had already happened to proactively guaranteeing quality from the start. Consider a high-speed soda bottling plant. The goal is to fill every can with exactly 12 ounces of liquid. But dealing with fluid dynamics at thousands of cans per minute guarantees microscopic variations in every single pour. To monitor this, engineers use a specific tool called a control chart. This chart shows the continuous data of individual soda fill levels, plotted against a flat line representing that 12-ounce average. Next, they calculate the upper and lower boundaries of acceptable, normal variation. These are statistically derived and known as the control limits. There is a golden rule to this chart. As long as the data points bounce around inside these two limits, the process is stable. The variation is just common cause noise, and the system must be left alone. But suppose a newly measured fill level suddenly jumps above that top red line. This breach is the early warning system firing off. It alerts operators that a special cause variation has occurred. They can halt the line and replace a failing pressure valve right now, rather than letting the machine churn out thousands of overfilled, defective cans. This methodology isn't restricted to physical manufacturing. Statistical process control applies to any environment that generates continuous data. Hospitals use these exact principles to track emergency room wait times. By plotting daily intake, administrators establish a mathematical baseline of normal patient flow. A spike past the control limits alerts administrators to a systemic break, like a localized outbreak or a scheduling failure, that requires immediate intervention. The math separates this specific, actionable signal from the usual noise of a busy Tuesday. Software engineers rely on the same charts to monitor server latency. By tracking the time it takes data to travel, they can identify special cause anomalies and reroute global internet traffic before a server gets overwhelmed and a website crashes. Whether you are managing patient flow in healthcare or data flow in cloud computing, the underlying mathematics of variation remain identical. This is an actual technical X-bar and R control chart used by engineers in the field today to track mean values and ranges. It plots live variations, clearly demarcating the safe operational limits from the danger zones. By rigorously tracking these points over time, Statistical process control takes a chaotic, unpredictable reality and distills it into reliable, actionable intelligence. It ensures that when things go wrong, we can see the exact moment it happens. It gives leaders the confidence to stop reacting to the normal background fluctuations and finally separate the true signal from the noise.